So we're talking now and for a month probably about groups. I'll give them a little star because groups are one of the most important things in mathematics. There's a very short, simple definition of a group, which defines in some technical sense exactly what a group is, but it doesn't give it full justice. So, so let me give the definition. A group is a set, I'll call it G, with a binary operation for example, some kind of, we might denote it by multiplication or addition. So that means, and I'll use multiplication as the generic operation in a group. Sometimes I'll write it additively, but and whenever I write something multiplicatively, you should understand that the same thing can be stated or defined with an additive notation. So we have this group, we can, if we have, and a binary operation means for any two elements in the group, there's something we call xy or x times y in the group. Such that the following properties are satisfied. First of all, the multiplication is associative. So we have the property of associativity. For all elements x, y, and z in the group, xy times z is the same as x times yz. So for example, multiplication of real numbers satisfies this, addition of numbers satisfies this, and so on. Second, the existence of an identity. There exists some element E in the group such that for all x in the group, E times x and x times E are equal to x. And third, we have inverses. For every x in the group, there exists an element y in the group such that x times y and y times x equals the identity. So a set with a binary operation that satisfies these three properties is called a group. If you have a set with a binary operation that's just associative, it's called a semigroup. And if you have a set with a binary operation that's associative and there's an identity, it's called a monoid. But we're not going to spend very much time talking about semigroups and monoids. The central notion is that of a group. Now, if we were to write these properties additively, in additive notation, associativity would say if you take x plus y plus z, that's x plus y plus z. And the existence of an inverse in additive notation would mean that e plus x and x plus e equals x. And the existence of an inverse in additive notation means x plus y and y plus x are equal to e. So this is how you would write these properties using additive notation. And that's it. Now, you know, they teach you in elementary school that 2 plus 3 equals 3 plus 2. They're 5, and 2 times 3 equals 3 times 2, there's 6. And if the binary operation in a group satisfies the following property, it's called an abelian or a commutative group. So if you have this commutative property, commutativity. So if for all x and y in the group, x times y is the same as y times x, then G is called the two terms which are synonyms, commutative or abelian group. So if this additional property is satisfied, the group is abelian. If you write this condition in additive notation, it would say that x plus y equals y plus x for all x and y in the group. Okay. Any questions about this? So let's look at some examples. Suppose we let R, this is a time sign, be the real numbers with 0 removed. So this is the set of non-zero real numbers. And in this set, multiplication, so the set of real numbers with multiplication, so let me just say this set is a multiplicative group because you can multiply, and they teach you that 7 times 5/2 times 19 is the same as 7 times 5/2 times 19. That's associativity. The identity element is just the number 1. 1 times 3 and 3 times 1 equals 3. And everything has an inverse. 7/2, what's the inverse of 7/2? 2/7. 2/7 times 7/2, 7/2 times 2/7 is 1. Every element has an inverse. So the non-zero real numbers with the binary operation of multiplication is a multiplicative group. And xy equals yx for all x and y in the non-zero reals means we have an abelian group. Okay. Any questions about this? Okay. What's another example? Z means the integers. 0, plus minus 1, plus minus 2, plus minus 3, and so forth. Under addition is an additive abelian group. The identity element is 0. 0 plus 7 equals 7 plus 0 equals 7. And the inverse of n is minus n, whether n is positive, negative, or 0. 7 plus minus 7 or minus 7 plus 7 is 0. So this is an additive abelian group. What's an example of a group that's not abelian? Well, let's see. Suppose we let G be the set of 2 by 2 matrices where A, B, C, and D, let's say they're integers, and the determinant, the number AD minus BC, is equal to 1. So I claim, and we give this group a name, is called SL2Z. The 2 means these are 2 by 2 matrices. The Z means the coordinates A, B, C, and D are integers. And L means special. What's special about these matrices is they satisfy this condition. So why is this a group? So the binary operation in this set of matrices is matrix multiplication. How do you multiply two matrices? We have the matrix A, B, C, D, and the matrix E, F, G, H. The multiplication is row into column. So if you multiply the first row times the first column, it's like taking a dot product of vectors. This is AE plus BG, AF plus BH, CE plus DG, CF plus DH. All right, that's what it is. I mean, if you have the matrix 1, 2, 3, 4 times the matrix, I don't know, 7, 9, 0, minus 2, what do you get? You get 1 times 7 plus 2 times 0, 1 times 9 plus 2 times minus 2, 3 times 7 plus 4 times 0, 3 times 9 plus 4 times minus 2. This is equal to 7. 9 minus 4 is 5. 21. 27 minus 8 is 19. So if you haven't had experience multiplying 2 by 2 matrices, now you will get the experiences. You just have to learn how to do it, just like you had to learn the times table in elementary school. So this is the product of these two matrices. And one can check, I'm not going to do it now, that matrix multiplication, as I just defined it, is associative. So for any three matrices, X, Y, and Z, your associative law is satisfied. The matrix identity, the identity in this group is the matrix 1, 0, 0, 1. And you can check that for any matrix A, B, C, D times 1, 0, 0, 1, whether you multiply the matrix on the right by this or on the left by this, you still get A, B, C, D. So we have this group of 2 by 2 matrices. The binary operation is matrix multiplication. This is an associative operation. There's an identity element. And what is the inverse of A, B, C, D? So suppose X is the matrix A, B, C, D. What is X inverse? Well, let me make a lucky guess. I claim it's always D minus B minus CA. You can work it out, but the best thing, just like the quadratic formula, is to memorize it. So what happens if I multiply X times X inverse? I have A, B, C, D times D minus C minus BA. So I get AD minus BC minus AB plus AB, CD minus CD minus BC plus AD. What is this? Well, minus A plus AB is 0, CD minus CD is 0. AD minus BC, I was only looking at matrices where AD minus BC is 1. And minus BC plus AD is the same as AD minus BC, so that's 1. So this is an inverse, at least when you multiply it on the left, And it's always important to do this calculation at least once in one's life. So suppose I multiply on the opposite, in the opposite direction. So suppose I multiply A, B, C, D on the left by D minus B minus CA. I get AD minus BC, BD minus BD, minus AC plus AC, minus BC plus AD. Again, I get 1, 0, 0, 1. So that's the inverse. So for example, if I take the matrix, I don't know, 7, 5, 4, 3. So in this matrix, A is 7, B is 5, C is 4, D is 3. And what is this determinant? AD minus BC. 7 times 3 minus 5 times 4 is 21 minus 20 is 1. So this is a matrix in this set of 2 by 2 matrices of determinant 1. And the inverse is going to be, you interchange the 7 and 3, and you change the signs of the 4 and 5. And let's just do the calculation to check. 7, 5, 4, 3 times 3 minus 5 minus 4, 7. This is 21 minus 20, minus 35 plus 35, 12 minus 12, minus 20 plus 21, 1, 0, 0, 1. We get back the identity. Okay. So this example is extremely important. It says this is a fundamental example of a group. And it comes up in many places in math and science, actually. And one of the important things about this group is that SL2Z is a non-abelian group. Non means not abelian. And let's see, how can we check that? Well, let me just take 2 sort of random matrices, 1, 2, 3, 4. Actually, what's the example I had started with? 1, 2, 3, 4. Um, 7, 9, 0, minus 2. So I already calculated this. 1, 2, 3, 4, 7, 9, 0, minus 2, 7, 5, 21, 19. Suppose I multiply, so this is, if I call this y at matrix S and this matrix Y, this is X times Y. And what happens if I multiply in the opposite order? 7, 9, 0, minus 2, that's Y, times 1, 2, 3, 4. So I get 7 plus 27 is 34. 14 plus 36 is 50. 0 minus 6 is minus 6, and 0 minus 8 is minus 8. And they're different. These are different matrices. So for this particular choice of matrices, XY is not equal to YX. In an abelian group, xy equals yx, no matter what matrices you pick, what elements x and y of the group you pick. So if there are two elements xy where xy is not equal to yx, that means your group is not abelian or not commutative. Any questions about this? So this is a really important group to understand. Okay, now what we do in algebra is prove stuff. So let's prove some things about groups. So this is a theorem in the notes that G be a group. The identity element is unique. There's only one identity element in a group. Every element has a unique inverse. The inverse element of a group is unique. And third, for all x and y in the group, if you take the product of x and y and take its inverse, this power minus 1 means inverse. That's equal to the product in the reverse order, the inverse of y times the inverse of x. So how do we prove this? So suppose that E and E prime are inverse elements in the group. So this means xe prime equals x for all x in the group. That's one of the properties of the identity, sorry, our identity elements. So if I take any element x and multiply it on the right by the identity E prime, I get x. And E times y is equal to y for all y in the group. If E is the identity, it satisfies this. So suppose we choose x can be anything, choose x equal to E, and y can be anything, choose y equal to E prime. So from this expression, x is equal to, sorry, if I let x equal E, E is equal to E times E prime. And if I let y equal E prime, E prime is equal to E prime. Done. That's the proof. So if two elements have the property of being the identity, in fact, they're the same element. So this proves one. What about two? Suppose x is an element in the group and y prime are inverses. So this means that xy prime is the identity and yx is the identity. Because y prime is an inverse of x and y is an inverse of x. So then I can write the following very pretty expression. Y is y times the identity. The identity can be written as xy prime by associativity, y times xy prime is yx times y prime. Yx is the identity, so that's e times y prime. And the e is an identity, is the identity. So this is y prime. So x equals y equals y prime. So we know that an inverse of every element x exists, and this proves that it's unique. There's only one, and we will denote the inverse of x by x to the power minus 1. And the last part of the theorem to prove is the following. Suppose I take the element xy times y inverse x inverse. I claim this is the inverse of xy, so this product has to be the identity. So by associativity, xy times this element is the same as x times y inverse x inverse. Here we're using associativity. Let me use associativity again. I'll use it in here. Y times this product is y inverse times x inverse. Y inverse is the identity. Anything times the identity is the anything. X inverse is E. So this proves that if I multiply xy on the right by this, I get the identity. And the same argument works if I multiply xy on the left by this element. This is y inverse, x inverse times xy. That's y inverse, x inverse x times y inverse e times y inverse y equals E. So that is the proof. Okay. Any questions about this? I mean, these are.
Can you please repeat?
Repeat what?
The last part.
The proof of this statement?
Uh-huh.
So I have elements x and y in the group, and I take the product xy. And what I want to show is the inverse of xy is equal to this. That means if I multiply this element by this element, I have to get the identity. So how do I prove that? Well, this times this, I can think of this is x times y times this element. So by associativity, that's x times y times this. That's just the associative rule. And here I have this times a product. Again, by associativity, I can parenthesize it like this, y times y inverse times x inverse. But y inverse is the identity. So I get x times e times x inverse. E times anything is the anything. So this is just x inverse. X inverse is the identity. And the same argument works if I do the multiplication in the opposite order. So what I proved is that the inverse of the element xy is y inverse times x inverse. It's not true in general that xy inverse is x inverse y inverse. In general, that's false, unless the group's abelian. So this is the true statement, and this is a proof. As we go along, the proofs get more complicated, but this is a sort of a basic proof, and you really need to study this thoroughly. This is written down in the notes that I posted on Blackboard in careful detail. There's some other properties of exponents that you're used to from doing math and calculus or wherever, and they're general statements that are true in any group. So suppose in the group G, let X be any element in G, and I want to define the powers of X. So let X to the 0 power be the identity. This is just like with ordinary numbers. 2 to the power 0 is 1. 1's the identity for multiplication. So in the reals, in general, we define, this is a definition, X to the 0 equals 1. X to the first power is X. X squared is X times X. But in general, for any n, X to the, if you have defined X to the n, X to the n plus 1 is X to the n times X. This is for n, a non-negative integer. So this defines the positive powers of X. We define X to a negative power, X to the minus n, as X inverse to the n. So X to the power minus 2 is X inverse squared. That means X inverse times X inverse and so forth. So we're defining the powers of X, and there is a theorem or a lemma in the notes that says the following. So X and G for all integers m and n. So m comma n, m and n in Z is the set of integers. X to the power m plus n is X to the m times X to the n. And let me just sketch part of the proof. So we want to show X to the m plus n is X to the m times X to the n. So let's do this for m equals 0. For m equals 0, this says X to the 0 plus n. That's just X to the n. And X to the m plus n, sorry, X to the m times X to the n is X to the 0 times X to the n. X to the 0 is the identity, and the identity is times anything is X to the n. So if you put this together, this X to the m plus n equals X to the m, X to the n is true for m equals 0. What about for m equal 1? So for m equal 1, X to the 1 plus n, which is the same as X to the n plus 1. By definition, this is X to the n times X. And X to the m times X to the n is X times X to the n. How do I know these are equal? So we're going to this, so the proof is going to be a proof by induction. So fix an integer m, let's say a non-negative integer m. And if you let n equal 0, x to the m plus 0 is x to the m. X to the m times x to the 0 is x to the m times e is x to the m. So x to the m plus 0 equals x to the m times x to the 0. That's kind of trivial. What about x equal 1, n equal 1? X to the m plus 1 by definition is x to the m times x. X to the m times x to the 1 is x to the m times x. So these are equal. So for n equal 1 is true. So suppose this statement is true for some number n, that is x to the m plus n equals x to the m times x to the n. So m is fixed. Suppose this is true for some n. What happens if you consider this when we replace n by n plus 1? X to the m plus n plus 1, this is x to the m plus n times x. That's how we define powers. This is equal to x to the m times x to the n times x. That's our induction hypothesis. By associativity, this is x to the m times x to the n times x. X to the n times x is x to the n plus 1. So I prove that this equals this. So if my statement is true for n, it's true for n plus 1, and this means it's true for all n. So this proves the theorem in the case of non-negative integers. And there's another argument you need for negative integers, which is written out in detail in the notes, and you can read it there if you're interested. So I don't know if there's a certain degree of culture shock in what we've been doing. So in mathematics, you prove stuff. Mathematics is trying to discover what's true by giving proofs, and that's what we're doing. And this is really a skill you have to learn. It takes, if you're not used to this, and even if you are used to it, it does take a lot of time going through proofs line by line and making sure you understand every statement. And then the best measure of whether you really understand it is if you can close your notes, close your books, sit down with a blank piece of paper and write out a proof. Write out the proof you've been studying. So my favorite group really is the integers under addition. And I can look at this set, I'll call it 2z, which is the set of even integers. So this is the set of all numbers of the form 2n, where n runs through the integers. This is 0, plus or minus 2, plus or minus 4, plus or minus 6, and so on. And 2z is closed under addition. They teach you the sum of two even numbers is even. 0 is an even number, is the identity when you're adding even numbers. And the inverse of an even number 2n is the even number minus 2n. So therefore, 2z is a group. It's a group contained in the bigger group Z. So If you have all the integers, that's a group under addition. If you look at the subset of even integers, that's also a group under addition with the same identity element. And this leads to the definition of a subgroup. Let G be a group with the identity element E. The subset H of G is a subgroup if it satisfies the following three properties. It contains the identity element of the group. If you have two elements in the subgroup, their product is in the subgroup. And whenever X is in the subgroup, its inverse is also in the subgroup. So this is the definition of a subgroup. What's another example? Suppose I let G be the non-zero, let's say, real numbers. Under multiplication. Let H be the set of powers of 2. So 2 to the 0, 2, 2 squared, 2 cubed, 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, and so on. This infinite set of powers of 2. So this is 1, 2, 4, 8, 16, all the positive integral powers of 2, but also the fractions, a half, a fourth, an eighth, a 16th, and so on. And this set of powers of 2 is closed under multiplication. I mean, you have 2 to the m times 2 to the n is 2 to the m plus n. So it doesn't matter whether your integers, your exponents are positive or negative. Product of two powers of 2 is a power of 2. The identity is 1. The inverse of 2 is a half. The inverse of an eighth is 8 and is 8. This is a subgroup. So I will pause for a minute just to take attendance, which I don't always do, but I do periodically. And you can think about what we've been doing and ask me questions in a minute. Let's see, Abdul Debray. Plumage. Meowie. Alba. Espinal. Alberto. Santiago. Duran. Edward and Edwin. Hernandez. Forch. Evariste. Valdrago. Sturgis. Sidibe, Acevedo, Acosta, Campos and Campos. Keynes, Cruz, Rodriguez, Sar, Gonzalez, Mona Alogo, Durame, Clark, Soto, Headley, Yu, Nasser, okay, got it. Any questions about what we've been doing? Okay, now there's another class of groups that are very important, and we're going to spend a lot of time on right away. Those are called permutation groups. So remember, you spend a lot of time in calculus studying functions. You could have a function f from x to y, and you could have a function g from y to z. And you can picture it like this. You have a set x, a set y, and your function f goes from x to y. And then you have a set z, you have a function g that goes from y to z. So if you take an element x in this set, it goes to some number f of x and y. And for every element in y, you can apply the function g to it, and you get g of f of x, which is in z. So if you start with x and you apply first f and then g, you end up over in z. And this operation of applying first the function f and then the function g is called composition of functions. Sometimes you write a little circle, g circle f of x is defined by this. So you know this very well from calculus. The chain rule in calculus tells you how to find the derivative of a composite function. And if we also have a function h from z to w, so we have x goes to y with f, y goes to z with the function g, and z goes to w with the function h. There's a composite function g composed with f from x to z. And if you compose that with h, you get a composite function h composed with g composed with f. So you have this function from x to w like this. But of course, it's not the only thing that can happen. You have also, if you have y goes to z and z goes to w, you have a function from y to w, which is h composed with g. And if you compose this with the function f, you get a different function from x to w, which is h composed with g composed with f. So these are two different functions, these superficially. And what can we say? For all x in the set x, if I take h composed with g composed with f of x, this means h of g composed with f of x. That's h of g of f of x. But this is exactly h composed with g applied to the element f of x, which is exactly h composed with g composed with f of x. So this equals this. And we have, this is actually a proof of the fact that composition of functions is associative. H composed with G composed with F is equal to H composed with G composed with F for all functions for which this makes sense. Now, suppose we consider functions f from x to x and g from x to x. So f composed with g is also a function from x to x. So suppose I let, I don't know, script f for function f of x be the set of all functions from the set x to itself. So f and g are functions from x to x, then f composed with g is also a function from x to x. So the set f of x is closed under the binary operation of composition of functions. The function e from x to x, defined by e of x is equal to x for all x in the set, is the identity under, is an identity under composition. If you take f composed with e of x, that's f of e of x, that's f of x. And E composed with f of x is E of f of x is f of x. So f composed with E and E composed with f is equal to f for all f, a function from x to itself. So this set f of x is closed under composition. We already proved a moment ago composition is associative. So with this operation, this set is a semigroup and it has an identity. But it doesn't have to have an inverse. Not every function has an inverse. So for example, if you take x to be the set 0 and 1, just two numbers, and f from x to x defined by f of 0 and f of 1 both get sent to 0, this has no inverse. Let me just say explicitly what the inverse of a function is. So that f be a function, the function g in f of x is an inverse of f if f composed with g of x and g composed with f of x equals x for all x in the set. So the inverse of a function is, well, here's an example. Suppose x is the real numbers, just like you do in calculus. And let's consider the function b, I don't know, f of x is the function 2x plus 3. Let me make a lucky guess. Suppose I let g of x be equal to a half x minus 3 halves. So this is also a function on the line. What is f composed with g of x? This is f of g of x. This is f of a half x minus 3 halves. When I plug this into the function f, this is 2 times a half x minus 3 halves plus 3. This is x minus 3 plus 3 is x. So f composed with g is the identity. What about g composed with f? That's g of f of x. That's g of f of x is 2x plus 3. That's a half 2x plus 3 minus 3 halves. That's x plus 3 halves minus 3 halves is x, which is e of x. So we also have g composed with f is the identity. So therefore, g is f inverse. Well, so here I have a function from the reals to the reals, and it has an inverse. That's what it is. But not every function has an inverse. For example, let f in this function on the reals be the constant function f of x equals 3 for all x. For every function g in f of r, if I take f composed with g of any number, I'll pick 2. This is f of g of 2. It doesn't matter what g of 2 is. Everything, f sends everything to 3. So f composed with g of 2 is equal to 3. It's not equal to 2. So f has no inverse. So this is just an important fact. It's sort of simple when you figure it out exactly, but not every function has an inverse. But you know that from calculus. Function has an inverse only if its derivative is always positive or always negative, for example. The parabola y equal x squared is no inverse. When does a function have an inverse? So we say that the function f from x to itself is, sometimes we say these are synonyms, 1-to-1, an injection. Sometimes if you're fancier, you say a monomorphism. All right. I mean, these are like 3 words which appear everywhere in the mathematical literature, but usually we'll just say 1-to-1 if different elements of x get sent to different elements of x. So if x1 different from x2 implies f of x1 is not equal to f of x2. So here we have the set x in this function. If you take a point x1, it goes to f of x1. If you take a point x2, it goes to f of x2. And if these points are different, these points are different. That's what it means to be 1-to-1. You say the function f is, and again, there are synonyms, onto, surjective, sometimes even epimorphism. These are the only words I'm going to use. If for every y in x, there exists an x in x such that f of x equals y. That says if you take any y in x, you can always find an x in x, which f sends x to y. And there could be more than one. There can be another element, x2, that also gets sent to y. But this function f sort of covers x because no matter what element in x you pick, it's always the image of some element under this function f. And a function has both these properties. If it's 1-to-1 and onto, well, 1-to-1 and onto. If f is 1-to-1 and onto. And again, this is called sometimes an isomorphism or an automorphism. Isomorphic. Or a bijection. And there's a fundamental fact about functions that we use right here, which says, suppose we have a function from x to y. This has an inverse if and only if f is 1 to 1 and onto. So here we have our set x, and here's x, and we have this function f from x to x. I want to construct a function g from x to x such that f composed with g and g composed with f are the identity. That means f composed with g of x equals x, and g composed with f of x equals x for all x in x. And how do we do that? Well, so that x be an element in x. We know, or that's called, well, call it x, doesn't matter. Say x prime is an x. Because the function f is onto, there exists an x in x with f of x equal to x prime. So there's some x over here that gets sent to x prime. And if we have another element, x2 in x, and f of x2 also gets sent to x prime, well, that can't happen. Then x2 is actually equal to x because f is 1 to 1. So what I've just proved is that for every x prime in x, there is a unique x in x such that f of x equals x prime. And we define the function g by g of x prime is equal to x. So f sends an element in x to an element in x. G sends an element back where it came from. So g composed with f of x, that's g of f of x, that's g of x prime, which goes back to x. And f composed with g of some x prime is f of x, which is x prime. So the invertible functions in f of x are the 1 to 1 and onto functions. And if f and g are 1 to 1 and onto, then f composed with g is also 1 to 1 and onto. So the set of one-to-one and onto functions of X is closed under composition. Composition is associative, contains the identity. The identity function is one-to-one and onto, and everything is invertible, is a subgroup of the set of all functions. And there's another name for a function from a set to itself that is one-to-one and onto. So it is called a permutation. The permutation of X is a function f from X to X that is one-to-one and onto. And we denote the group of permutations of X by perm of X. And a very important special case of a permutation group is the following. It's the case that occurs when the set X is a finite set consisting of just the first n positive integers. So the set of, or the group of permutations of the set of the first n positive integers is called the symmetric group. And it's denoted S sub n. So for example, S2 is the set of permutations of the set 1, 2. Now, there are only two of them. So we have the identity function, E of 1 is equal to 1, E of 2 is equal to 2. And then we have the function, I'll call it sigma. I like Greek letters for permutations, defined by sigma of 1 is 2, and sigma of 2 is equal to 1. So S2 just consists of these two permutations, the identity and the one that's interchanges 1 and 2. If you let S3 be the set of permutations of 1, 2, and 3, there are more of them. So we have the identity defined by E of X equals X. We have, let's say, the permutation, I'll call it sigma 1, which is defined by sigma 1 of 1 is 2, sigma 1 of 2 is 3, sigma 1 of 3 is equal to 1. That's a permutation. Or I have sigma 2 defined by sigma 2 of 1 is 3, sigma 2 of 2 is 1, sigma 2 of 3 is 2. So these are interchanging these numbers. And I could also, like, for example, fix 1 and define the permutation tau 1. Let's say tau 1 of 1 is 1. Tau 1 of 2 is 3, and tau 1 of 3 is 2. So this keeps 1 fixed and interchanges 2 and 3. I have 2 more. I could let tau 2 be the permutation that fixes 2, but interchanges 1 and 3. And tau 3 would be the permutation that fixes 3. And interchanges 1 and 2. And if you work it through carefully, you'll see this is all there are. So S3 contains exactly 6 permutations, the identity, sigma 1, sigma 2, tau 1, tau 2, tau 3. So this is a very nice group. And let me just write down the fact that there is a standard representation of a permutation sigma in Sn. So sigma is a function from the first n integers to itself. So I can write down this sort of 2 by n matrix, 1, 2, 3, 4, 5, up to n. And so here I have the numbers 1 to n, and under it I put the numbers that sigma sense, like 1 goes to sigma of 1, 2 goes to sigma of 2, 3 goes to sigma of 3, and so forth. So for example, if I look at this, 1, 2, 3, 2, 3, 1, this is a permutation in S3. And this means that sigma of 1 is 2, sigma of 2 is 3, sigma of 3 is 1. So this is standard representation of a permutation. So permutation groups are really important groups, and I would strongly encourage you to invest a lot of time in studying them. And there's quite a bit in the chapter 2 of the notes that I posted about permutation groups, and you really need to study it very carefully and do a lot of problems involving permutations. So as algebra goes, this is very concrete. These are they just involve finite sets of integers, and it's like something to study. Okay. Any questions about this?